Welcome back to another discussion in Calculus 2, where we're going to continue our journey in Chapter 9. We've introduced this idea of series in the last couple of videos, where we're taking a sequence, which we defined at the start of Chapter 9, and we are adding up all the terms of that sequence. And the question is, well, when we add up all of these terms, now there's infinitely many terms to add up, we have an infinite series of things. When do I get something finite back? Is there a way, or are there certain cases in which I can add up infinitely many terms and still get something finite? If that happens, we call that a convergent series. If not, we call it a divergent series. And so we want to understand, when given a sequence, when we ask to add it up, construct what we call the series, when will it converge and when will it diverge, in what cases? And we introduce two types of series, two special series in which we could actually explicitly figure out what we call the partial sums. Remember, that's how we do it. We add up a single term at a time. We add one more term. We create a sequence of partial sums and ask ourselves, where are these partial sums going to? And if those partial sums converge to some number, that is then the actual sum of the entire series. So it all comes down again to limits of sequences. In this case, it's sequences of partial sums. Now, while we looked at two series in which we could construct these partial sums, we looked at telescoping and geometric. In general, finding a formula or a function that models the partial sums of a random sequence is not something that we necessarily want to try to undertake. And so what we're going to do now is we're going to transition and say, okay, let's not worry about trying to find the partial sums and a formula for the partial sums. Let's instead try to answer the question using calculus or using other tools that we need without having to directly find the sum of the series. And therefore, we're going to get answers that are now just converge or diverge, and we're not necessarily going to know what the sum actually is. With telescoping, you have the formula for the partial sum, so you take the limit and your answer is the sum of the series. With geometric series, remember there's an explicit formula for the sum of a geometric series, a convergent geometric series. Here now, we're not going to have formulas for sums. We're not going to have a partial sum formula. Instead, we're going to use some other tools from calculus and from algebra and geometry to help us try to figure out how we can answer this question without having to go down that route. And so what we're going to introduce first is something that's familiar to us. We're going to introduce integrals and how integrals and integration, the integration we learned in calculus, can help us answer this question. And so we call this the integral test, very non-unique name, the integral test. And out of the integral test, we're actually going to get another special type of series, which we call a p-series. It's a type of series that fits a certain format in which we can always get an answer to the question without having to integrate some things. And so in general, what's the idea of the integral test? Well, let's start out with the sequence. So let a sub n be a positive and decreasing sequence. And let's say we have some sort of function, f of x, a continuous function on 1 to infinity, that agrees with my sequence everywhere. F of n equals a sub n for all n. That just means, right, we've played connect the dots, and this function agrees with the outputs of my sequence for all n. And we kind of have this nice red curve that connects all of my sequence terms together. And so we construct this nice continuous curve, f of x. How are integrals going to come up to play? Well, I'm going to ask us a question that is kind of complicated in the way I ask it because it kind of breaks down what we know so far in calculus, but we'll still be able to answer it. Is I want to integrate the red function, this continuous function on 1 to infinity, from 1 to infinity. I want to create this integral. The definite integral of this function from 1 to infinity. Now, since this is positive and decreasing, my function is then positive and decreasing. We're always above the x-axis, so I can call this area, in fact. Right? This is the area under the curve. And so really, we're asked to find the area under the curve of this function from 1 to infinity. Now, the upper limit of the integration should be what scares you because, right, we have never integrated off to infinity before, but we're going to address that today. So I want the area under this curve from 1 to infinity. Now, if you remember how we developed integration, you remember that the way we formed or developed this symbol and where we got it from was this idea of infinitely many, infinitely thin rectangles. Well, let's not go down that road. Let's not go down the road of infinitely many, infinitely thin. Let's be very discrete. In fact, let's put certain rectangles underneath this curve. My rectangles are going to have a consistent base of 1. So the bases of my rectangles are not infinitely thin. The base of my rectangles are going to be 1. I'm going to use the left endpoint for my heights. We'll see what happens when I use the right endpoint, but right now I'm going to use the left endpoint for my heights of my rectangles. And so that means the height of the first rectangle is A1, the output of the sequence at 1. The height of my second rectangle is A2. The height of my third rectangle, A3, A4, and so on. And so if we actually look at the areas of these blue rectangles, well, one, you notice that the area of the blue rectangles is always larger than the area of the red. And so if I were to add up all the areas of the blue rectangles, whatever that sum is would be greater than whatever the red area is, because these rectangles are always above it. Now, what is the area of each one of these rectangles? What's the area of that? That would be the base times the height, but the base is 1, the height is A1, so A1. What about this second rectangle? The base is 1, the height is A2, base times height gives me A2. The next one would be A3, right? Because the bases are all 1, so the heights then are just the areas. 1 times A3, 1 times A4, 1 times A5. And then I add up all of these rectangles. Well, it turns out if I add up all of these rectangles, we get an infinite sum of rectangles. In fact, an infinite series. All the rectangles are AIs. And so we have n from 1 to infinity, a sub n. This would be the areas of the rectangles. This would be the area under the curve. And now we get a very definitive inequality, and we'll play it safe, we'll put it or equal sign, but we notice that these blue rectangles are always above this red area because it's positive and decreasing. And so what we can say is that the sum on this side, the area of the rectangles, would then have to be greater than or equal to the area under the curve. So on one hand, we have this infinite integral, right? This integration from 1 to infinity, if this number exists, is going to be less than or equal to the actual sum of all of the rectangles, which is my series. So this is how series are going to come into integration. Right now we have this inequality. Now let's go on the other side. What happens if I use the right endpoints instead of the left endpoints? And so again, we have the area under this curve from 1 to infinity. This time, since I used a right endpoint, all the rectangles you notice are all underneath this curve. The areas of these rectangles, though, are still, well, this one's A2, right? Because we used the right endpoint. A2 times 1, base of 1, gives me A2. A3 times a base of 1 gives me A3. A4, A5, A6, dot, 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 dot. And so what we can say now is, well, then the series from 2 to infinity of a sub n, that sum, on the other hand, would be smaller than the area under the curve. These rectangles are underneath it. So we'll say inequality now going the other way. Now we notice the integral still starts at 1, right? The integral is still at 1. I just use the right endpoint for the rectangle, so that's why the sum here starts at 2. But here comes the nice idea. Is that if, on this side, now go back to this one, if this integral diverges, meaning it doesn't give me an answer, it blows up, it doesn't converge to anything, then this series is larger or equal to this sum, the sum in question. Well, if I know something about the integral, I can get an answer about the series, because if this integral diverges, then that means that this series must also diverge. Why? Because it's larger than this integral. Nothing larger than infinity, but infinity itself. So if this sequence, or if this integral diverges, then we can say this series itself diverges. Now let's go on the other side. One thing also to notice about this inequality, right? We have my integral is greater than or equal to the sum of all of these rectangles. It's very important that my series is positive and decreasing, meaning I'm always above the x-axis, so we can say we are bounded below by 0. So it's smaller than this integral, but of course still positive, right? We're all above the x-axis, right? We're not going to have rectangles underneath, so we're not going to have to cancel out anything and get negative answers. So it's at least bigger than 0, but smaller than that integral. Well, what that means now in this case is that if this integral, this infinite integral, converges, say it gives you something finite, then the series, now from 2 to infinity, would also converge. Gives me something finite. It's going to be positive and less than this integral. Well, this is finite, so if you're smaller than a finite number and positive, you must also be finite. So we must be finite as well. The series would then converge. Well, if the series from 2 to infinity converges, we'll put in a note, this implies 1 to infinity converges. So we're not going to worry about the 2 to infinity, because if 2 to infinity converges, me adding one more finite number to it is not all of a sudden going to make it blow up, right? A1 is some just finite number, right? It's the output of the first natural number, right? Plug 1 and you get a number back. And so if the sum from 2 to infinity is finite, adding the a sub 1 in is not going to change the convergence of it. And so what's the conclusion here that we have is we get a direct comparison between integrals and series. On one hand, if the integral diverges, then the series diverges. We also have that if the integral converges, then the series converges. So if we want to answer the question about a series, we can get an answer by looking at a kind of continuous version of the problem, right? Instead of a discrete sum, a continuous sum. Instead of a discrete function, a continuous function. Now from 1 to infinity continuously, and so on. Now the only thing to address before we write down the integral test and start working with it would be, okay, that's great, but how do I work with this infinite integral, right? This idea of integrating from 1 to infinity. And it's just a little workaround. It's not anything crazy that we need to do. If we're working from 1 to infinity, f of x dx, we use the fundamental theorem of calculus. We would want to find an antiderivative and plug in the endpoints, but of course you can't plug in infinity. And so the workaround for this is to introduce a limit. Instead of going from 1 to infinity, go from 1 to t. Now you can use whatever letter you want. I'll use t for my variable, f of x dx. And now there's no problem with taking an antiderivative, plugging in t. So I'll get an answer in terms of t. Antiderivative, plug in 1, I'll get a number, take that difference, I can do it, and then all I would need to do is let t now go off to infinity. So since I can't plug infinity in directly when I take antiderivatives, I'll just do it one step at a time. I'll replace my x by t, and then let t run off to infinity, and therefore answering this question. So this is how we're going to tackle those infinite intervals of integration. And so from this, we get what we call the integral test. So the integral test is our comparison between series and definite integrals, or in this case, infinite intervals for my definite integrals. And so I wrote the integral test over here for us, and we'll get some work with it. So the integral test tells me that given a sequence that's positive and decreasing, and we have some sort of continuous function that agrees with my sequence on 1 to infinity and is continuous, then this is just saying whatever happens to the integral is what's going to happen to the series. If the integral gives me something infinite, if it blows up, if it diverges, then the series would diverge as well. If the integral converges, then the series would converge as well. So whatever happens to the integral is what's going to happen to the series. Now, in this setup, in this test, we're in no way trying to find the partial sums. We're not actually trying to get what this sum is. And so I'm not going to know the sum of the series. I will know the integral if it converges. But the integral, remember, is not exact, right? It's like an approximation of the actual sum of the series. So you could say that the integral is close to what the sum of the series is, but it's not the actual sum. And so we're not going to be able to find the actual sum. Our answer will now just be like converge or diverge. You won't be able to tell me the sum. And so we put this into practice. And so here are a couple examples of series that are not telescoping and are not geometric. We don't have this nice cancellation where we just end up with a finite number of terms and we can find the partial sums and take the limit. It's not geometric either, right? It doesn't fit the exponential format of a, r to the n, where now we just need to look at what the value of r is. In this case, we have a rational function. In this case, we have kind of an exponential function, but it's with a polynomial there, so it kind of messes me up. However, both of these functions, both of these sequences, can be modeled by continuous functions that I can integrate. And so let's think about this function here. And let's think about this function here. Both of these functions would obviously agree with my sequence at all natural numbers. They're continuous from 1 to infinity. There's no issues plugging in positive numbers from 1 on. And so let's try to answer the integral version of this question. Now we can use the antiderivatives, the fundamental theorem of calculus, and hopefully get an answer. Now, because of the whole infinite thing here, we don't like that upper limit of infinity. All I'm going to do here is replace infinity by the letter t and let t go off to infinity. So I'm still bypassing my rules of integration by kind of faking my way through. I'll integrate from 1 to t so my integral doesn't get upset at me, and then I'll let t go off to infinity and therefore get the answer that I need. Now we just do everything that we know from calculus. In both of these cases, it's a very nice U-substitution problem. Here, if you let u be x squared plus 1, du is exactly the numerator here, 2x dx. So it's a nice U-sub. Here again, it's not a bad U-sub. If I let u be x squared, that exponent of x in the denominator, then du is 2x dx. Now, I don't have the 2x in the numerator, but that can be adjusted like this. And so we do our substitution. We get the limit as t goes to infinity. The numerator is now just du, 1 du, and the denominator is u. So we get something that looks like this. Now, of course, we need to remember to change my bounds. So when x is 1, u is now 2. When x is t, right, we get t squared plus 1. So when x is t, we get t squared plus 1. Same thing over here. We'll do our substitution. We get the limit as t goes to infinity. We have a 1/2 out front because of the lack of the 2 right here. The 2x dx becomes 1 du, and again we get the same type of integral, 1 over, but not 1 over u, 1 over e to the u. And now, of course, we need to change our bounds. When x is 1, u is t, or u is 1. When x is t, u is t squared. And the limit as t goes to infinity, right? So we're just changing our bounds like we normally do. We do my U-Substitution. We evaluate these integrals. And then we'll take the limit. Limit as t goes to infinity. We get ln of the absolute value of u, evaluate from 2 to t squared plus 1. On this side, we get the limit. I'll bring the 1/2 out front. Limit as t goes to infinity. Antiderivative of 1 over e to the u. Remember, it's not always ln. Just think of this as e to the negative u. And actually, this is now negative e to the negative u. From calc 1, not too bad. Think of this as e to the negative u. And then you could either do another u sub if you want, or just realize e to the negative u is going to be negative e to the negative u because of the chain rule. And here we're evaluating from what? 1 to t squared. Let's go back over to this one. Limit as t goes to infinity. Plugging in t squared plus 1, ln of t squared plus 1 minus ln of 2. Over here, we get 1/2. Limit as t goes to infinity. Negative 1 over e to the t squared minus negative, so plus 1 over e to the 1, so 1 over e. Now we're not done because we took the definite integral, we used everything we know from calculus. Now we're going to take this limit and then we're going to get the integral that we want, right? The infinite integral. If we let t go off to infinity, understand that ln is very slow but still increasing function. And so ln of infinity, this is going to blow up, blows up to infinity. So we get infinity minus ln of 2, which is of course infinity. That's not good for the integral, and that's not good then for the series. So what this tells me is this integral blows up. This integral blows up to infinity. It does not converge. This integral diverges. And by the integral test, if my integral diverges, then the series would diverge as well. And so my answer here is that this series diverges. It does not converge. The sum of that series is not a finite number. Here, let's take this limit. Now here, we get something interesting because if we let t go off to infinity, even though that exponential blows up, it's in the denominator. And actually, I'm going to get 1 over infinity. That is not infinity. It's not indeterminate. That goes to 0. And so we're going to end up with 1/2 times 0 plus 1 over e. Well, that's 1 over 2e. 1 over 2e is my answer. That's a finite number. Since I got a finite number, that means this integral converges. You gave me something finite. And looking at my integral test, if the integral converges, then the series would also converge. And so my answer here is that this series converges. The sum of this series is a finite number. What is this finite number? I do not know. It's something close maybe to 1 over 2e. That's the integral answer. But I don't know the series answer per se. But I do know that it is a finite number. And so this is an example of using the integral test. The idea is, hey, this is not telescoping or geometric. However, I can write this as a continuous function and consider the integral version of the same problem, right? The continuous version of this problem. And if I answer the question about the integral, whatever the answer for the integral is, diverge or converge, will be the same answer for the series itself. And so that's how the integral test works. Now in the next video, what we're going to do is we're going to look at a very specific type of function involving the integral test. And out of that certain type of function, we're going to get what we call a p-series. And so in the next video, we'll wrap up the integral test by looking at p-series.